welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge. All right, hi everyone. Welcome to House of ZK's Bitcoin series special with Robin Linus. Robin is quite an innovator. He created BitVM, ZeroSync, ZK Coins, Bitstream, to name a few. But thank you so much, Robin, for being here today. I'm really excited to hear about the need for more programmability in Bitcoin and some of the design considerations behind BitVM. I'm wondering if we can first start off with an introduction of yourself. I'm curious to hear more about your background and also your why into getting involved in the Bitcoin space. I know you come from a software engineering and applied cryptography background, so I was curious to hear about your transition into the Bitcoin space and why you've kind of stayed involved in this space after so many years.
Yeah, first of all, thanks for having me. Why I'm in Bitcoin? Well, I think the monetary system is broken. I think fiat money is quite an issue and to the disadvantage of most people. And I'm one of the crazy people who believe that Bitcoin could be a solution to that. I know that the probability that it actually works out is quite low, but I think it's worth trying, and that's why I dedicate my work time to that.
Yeah, absolutely. Fiat money right now, as you say, is an issue. There's a lot of problems with our traditional ways of handling money and payment. And Bitcoin originally was made to be for payments. And I know that you are very much a huge proponent into further advancing its adoption. But from here, I'm wondering if you could talk about the need for Bitcoin to become more programmable and how it'll affect Bitcoin's traditional narratives. Well, traditionally, it was made to be a peer-to-peer payment system, but in recent days, it's been used a lot or as a store of value, and people view it as digital gold. So wanted to hear about from your side, what is the need to make Bitcoin more programmable and enable for some more, especially relating to payment-related use cases?
So I personally do not care that much about making Bitcoin more programmable in the sense of like adding more smart contracts and so on. I care about scaling Bitcoin as a means of payment in particular. And yeah, since layer one doesn't scale at all, I think 10-minute block time and like 4 megabytes per 10 minutes is, of course, by far not enough for the entire world to transact on Bitcoin. And that's why we need other solutions to scale Bitcoin. And we have seen on Ethereum all these L2s that are based on like ZK rollups, like snarks essentially. And I wanted to see that on Bitcoin as well. And a byproduct of that is that you can build more expressive L2s as well that have more programmability and that enable all these smart contracts and like automated market makers and like lending protocols and all these things that you see on Ethereum and the other chains.
Got it. So the expressibility aspect, the programmability aspect, you see it as more of a byproduct, but your main focus here is scaling Bitcoin as a means
Yeah,
of payment. Mhm.
I think other
Got it.
people see it the other way around. People wouldn't be as excited about BitVM if it would not enable all these smart contract applications. Um, but I personally think the payments use case is the most important, and also enabling privacy because I think that's fundamental for payments.
Absolutely. And wanted to hear from here how that has led to the creation of BitVM and BitVM's current design. Also wanted to hear more about what makes BitVM unique compared to, say, some of the other existing constructions or proposals for performing computation directly on Bitcoin and enabling for trust minimized bridging. Like I know, for example, Starkware has their own Collider VM construction. There's some other BitVM like proposals out there. So I wanted to hear about, how all of this led to in terms of wanting to scale Bitcoin's computation. How does that lead to BitVM's original design and how it compares to some of the other constructions that exist?
Well, originally the best we had was just multi-sigs, and they're of course not very satisfying. They have poor trust models, and yeah, the grand vision was to somehow hack a ZKP verifier into Bitcoin, because once we have a ZKP verifier, we can build bridges, and then we can build second layers, and then we have all the good stuff like scaling and programmability and so on. And the first thoughts were like, can we somehow have a super compact ZKP verifier such that it's small enough to just implement it in Bitcoin script? But it turned out that this is by far not possible, or at least none of the people who I've been working with had figured out any way to get even close to that. And then over time, this idea came up of using a optimistic approach, of using like optimistic verification. So you do not actually execute the snark verification, you falsify a snark verification. So you have essentially two parties. We call them like an operator, the bridge operator. And that operator, he just posts a snark and he claims that it is correct. And if it is incorrect, then you can succinctly disprove them. And this is way more efficient. A common example for that is, for example, if I give you a Sudoku solution, it's much easier to, it's much harder to check that the entire solution is correct than to show that it's incorrect. To show that it's incorrect, you would just have, let's say, one column is incorrect, and incorrect would mean some number repeats in there. You always have to fill in the numbers from 1 to 9. And if some number repeats, then you just show me two cells, and that disproves the entire solution. So just showing two cells is sufficient to disprove the entire solution, while checking the entire solution, you would have to check all of the cells. And that shows that in general, it is possible to, or like it's often easier to disprove a incorrect result than to actually verify the correct result. And we are using exactly that mechanism to optimistically verify a snark. So you provide a snark, and if it's incorrect, then you can succinctly point out the error in the snark. And it turned out that this is actually efficient enough to do it on Bitcoin within all the crazy constraints of Bitcoin script. Most people are not aware how constrained Bitcoin script is. Like you cannot even do multiplication in Bitcoin script. Like we have to hack that together with like many additions and stuff like that. And it's just 32-bit arithmetic. So if you want to do like 256-bit arithmetic, you have to do like a lot of opcodes, and I think it's 70,000 opcodes or something for a single multiplication. Yeah, but it's still possible. Like doing all these hacks at the end, it is actually possible to optimistically verify a snark, and that enabled BitVM, and that enabled this idea of building trust minimized bridges that in the end rely on like an honest existential honesty assumption instead of an honest majority assumption. So just a single party suffice, and a single honest party sufficed. And yeah, that created a whole new field of research, I would say. And a lot of these tricks that we use, for example, using Lamport signatures to introduce state and stuff like that, they inspired people to apply them in different ways. And you've mentioned, I think, Collider VM, like Starkware's idea. That is very interesting from a theoretical point of view, but I think it's not quite practical. It requires finding hash collisions that are kind of expensive, and it is doable. Like it's not like absolutely out of this world, but I think it's not practical enough for them actually to launch it. I might be wrong, but that was my impression when I heard about it. And yeah, what other systems did you want me to talk about?
Oh, no worries. I think that's a great enough overview. And
Mhm.
it's really good that you also mentioned kind of the original um, point that you have with optimistic verification and how that led to the creation of BitVM. So um, you mentioned that it's a lot harder to check if the entire solution is correct rather than pinpointing, say, an incorrect solution, pinpointing the exact error, say, as opposed to revealing the entire execution trace that proves the correctness of, say, a snark. So great to hear the origins from there. And yeah, it sounds like Bitcoin script is a lot has a lot more limitations. You even mentioned for like a single multiplication. Sometimes it can take around 70,000 opcodes as well, which is quite a lot. But yeah, it's really great to hear how much you and um, the collaborators you were looking at, you were working with, were looking at all of these different tricks. You even mentioned the Lamport signatures as well. All these tricks to help with the efficiency component. So that's all great to hear. And I wanted to also ask you about some of the more recent developments, specifically with BitVM 3. So what kinds of improvements were made on BitVM 3 as opposed to some of the other prior BitVM designs? Like for example, I think one of BitVM 3's main components is the use of garbled circuits that really help to address the efficiency component. Um, Previously, some of the larger on-chain transactions were a few megabytes long. I think you mentioned that in the beginning when you were introducing yourself, which is quite expensive on Bitcoin. So wanted to hear about some of the improvements that were made specifically on BitVM 3 that improve maybe some of the limitations of prior BitVM designs.
Yeah, so in BitVM 2, the like it is practical, but the worst case is very expensive. As long as everyone is honest and the incentives work out, it's cheap, but you still have to be able to pay for these very expensive transactions, and that requires a lot of collateral, and that makes the entire system quite expensive. Um, as you said, like the transactions can be up to like multiple megabytes, like 4 megabytes or so. So an entire Bitcoin block full of script. And then you have to be able to pay for that, of course. And that was one of the major downsides of the BitVM 2 approach. And BitVM 3, the key insight behind it is that you can use garbled circuits for something we call conditional disclosure of secrets. So you disclose a secret under a certain condition. And the condition here is actually if you provide an incorrect snark. Like if you provide a faulty snark, then the garbled circuit, um, or maybe the garbled circuit is actually a snark verifier circuit. Yeah? And a snark verifier essentially it takes a proof and it returns true or false. Uh, either either the proof is correct or it's incorrect. And if the proof is incorrect, then this garbled circuit reveals the label, a secret for false, for the return value false. And knowing that secret is a fraud proof. So if I provide a proof, you feed it into that garbled circuit that we exchanged during setup. And if it's incorrect, then you learn the output label false, and that is a fraud proof. And this is just like 20 bytes or something. It's just a hash pre-image, and this allows you to prove to the chain that I provided an incorrect proof. And so the slashing mechanism boils down to just revelation of that pre-image. And that is, of course, orders of magnitude cheaper than what we did with BitVM 2. In BitVM 2, we had to execute at least a chunk of the computation, and it was like up to 4 megabytes of script. And here we just have like a 20-byte hash pre-image that you have to reveal. And that is, of course, a huge improvement in terms of on-chain efficiency. However, it comes at certain trade-offs, in particular like the off-chain communication or the off-chain cost. Because if you just naively implement a snark verifier in garbled circuits, it turns out that it's like on the order of almost a terabyte of garbled circuit. And also we need verifiable garbled circuits. So when I give you that garbled circuit during setup, I have to prove to you that it's actually a snark verifier circuit and not just like some random gibberish. So to make it verifiable, you have to prove the entire circuit, and if it's like a terabyte of data, it becomes quite expensive to prove it, of course. And yeah, there are like once the BitVM Alliance, like all the companies that work on BitVM, got garbled circuit pilled, the research around it exploded. Like people very quickly explored all kinds of directions and tried to solve this problem of this enormous off-chain cost. And now there are many different solutions. There's like the traditional solution, I would say, that is called just YAO style garbled circuits. That is essentially the same thing that was originally invented in the 80s or so. And you can optimize it a lot with tricks that are called like free XOR gates, for example. So the XOR gates, you can actually implement them such that you don't have to do any communication. So the size of the garbled circuit doesn't grow with the number of XOR gates. And then you have stuff like so-called half garbling. That means instead of having 4 ciphertexts per gate, you just need a single ciphertext per gate. That reduces the circuit size by roughly 75%. And yeah, then you can do all kinds of optimizations on like the CPU level to garble faster. And yeah, the verification is still an issue. You cannot just throw it into a Stark prover or something, because it's still gigabytes of data and lots of hashing, and it's very proof unfriendly. So people resorted to using a relatively simple technique that is called cut and choose. That means instead of just garbling one circuit, I garble multiple circuits and commit to them, and then you choose a subset of them, and then I just reveal all the other circuits to you, which is cheap because I can just reveal the seed, so I don't have to send you all of the circuit. I just send you the seed, and then you can check that I actually garbled them correctly. And then I just send you that subset that remains. Let's say you garble, I don't know, 200 circuits or something, and I reveal to you 193 or so, and then 7 will remain. And there is a very high probability that they are correct. If the 193 were correct, then it's very likely that at least one of the 7 remaining ones is also correct. I think the probability is 2 to the power of -40 or something. So that's reasonable, since you cannot grind or something. It's not like a hash function where you could like do millions or billions of attempts. Here you just have a single attempt, and if you would abort the protocol multiple times, it would become very obvious that you're cheating. So this probability is suffices in practice. And yeah, that makes it quite practical in the end, because we don't have to do the proving anymore. We just use that simple technique to make the circuit verifiable. And this is like all the classical techniques, I would say. And then there is that amazing breakthrough by Liam Egan. He came up with a new scheme that he calls GLOC, like garbled locks. And he did a few interesting improvements. First of all, he used a so-called designated verifier snark. So a snark where the verifier is a designated person. Usually anyone can verify a snark, but here you have a designated verifier, which in the setting of BitVM is fine because there's also a designated set of challengers. So challenging is unfortunately permissioned. And since there is already a permission set of challengers, we can make them designated verifiers of the snark. And once you use designated verifier snarks, you have the advantage that you don't need to use pairing-friendly curves anymore. You essentially get rid of, you can emulate KZG commitments without pairings, essentially. And that means you can use any curve. And that means in particular you can use curves over binary fields. And that is extremely efficient in combination with garbled circuits, because in binary fields, like the field operations, in particular addition, is essentially XOR. And since we have that free XOR technique, most of the operations become free. To give you an idea, in like the classical snark, like the Gross 16 snark circuit that we have built, it has on the order of 10 billion gates, and I think 7 billion gates are free gates, so they're XOR gates or not XOR, and there are a couple other free gates, but in general you can think of them as XOR gates. So it's roughly a 70% reduction, but in Glock you still have on the order of 10 billion gates, but you only have 10 million non-free gates. So 99% or more is free gates, because you're using this binary field, like binary this field over, sorry, a curve over a binary field, where the base operations are essentially just XOR. And this improves like the everything by orders of magnitude. The circuit becomes much smaller, and you can verify it much quicker, or you can prove it much quicker, and essentially it becomes way more practical. And also Liam came up with a couple other tricks to optimize the on-chain cost, because you still have to commit to the proof on-chain, and you essentially have to Lamport sign it. So essentially for every bit you have to reveal a hash preimage, and that is roughly on the order of 70 kilobytes, naively. And Liam came up with a couple tricks using so-called adapter signatures, and they reduce it to 10 kilobytes roughly. So if you compare that to BitVM 2, where you had like we have these two transactions, the assert transaction and the disprove transaction. Assert transaction is where the operator asserts to a proof, and the disprove transaction is where a challenger can disprove the asserted proof. And in BitVM 2, the assert transaction was roughly 2 megabytes, and the disprove transaction was roughly 4 megabytes. And in BitVM 3, or like in garbled circuits, the assert transaction is now 10 kilobytes instead of 2 megabytes, and the disprove transaction is roughly 200 bytes instead of 4 megabytes. So that's orders of magnitude better, and that's why everyone is super excited about it now.
Yeah, got it. Thank you so much for that. For that overview. So it seems like for the garbled circuits approach, at least for the hash pre-image to reveal, it's only around 20 bytes long. But there are some trade-offs in terms of some off-chain costs that are incurred, making also those garbled circuits verifiable and needing to prove that entire circuit, which if it's around like a terabyte long, could be quite computationally intensive. But you mentioned some of the solutions around that, like the traditional style ones. You mentioned about the Yao style garbled circuits, and then also that approach of having that single ciphertext per gate, and then even like the Glock solution that uses the designated verifier snarks, as well as even some other tricks relating to those about adapter signatures. So it's really great to hear kind of all of the work and all of the
Verified is very
innovation.
sorry, the
Mm,
1 terabyte is really like the most naive approach. Already the classical optimizations like free XOR and half garbling, they bring it down to, I think, on the order of 50 gigabytes per garbled circuit.
got it. Okay. So that's like quite a reduction. And then even with those additional tricks, that's even more
Yeah.
of a reduction with the circuit size. Okay. Yeah. So it's really great to see kind of all of these different optimization techniques and tricks that different teams are looking at to try to reduce that overall circuit size and try to address those on-chain costs as much as possible. So that's great to hear. And from my understanding, BitVM3 also proposes a new kind of hash function that's optimized for the script. So the bit hash function. So I wanted to hear from you what kinds of properties BitHash provides and like what particular types of scenarios the BitHash function would be more ideal to use compared to some of the standard hash functions. You mentioned like some of the transaction types that are compatible with BitVM. So perhaps like during an assertion transaction, or if you see any other kinds of scenarios where it would be very optimal.
Yeah, that is already kind of outdated, I would say. Like originally, it was an issue to make the circuit verifiable. Like even this cut and choose method, it was way too inefficient in the beginning. So we thought about other ways to make it verifiable, and there is that idea by Jeremy Rubin. He came up with a paper called Delbrag, like garbled spelled backwards, and there the idea was that you essentially use optimistic verifiable garbled circuits. That means like I give you a garbled circuit, but I also commit to that garbled circuit in a taproot. And if during evaluation you learn that any of the gates has been garbled incorrectly, then you can prove that to the chain and slash me. And his approach was a bit inefficient because, well, like you need to evaluate hash functions to do that. But the problem is that you have to also work on the pre-images. And that is an issue in Bitcoin script in general. Like there's that thing called big script and small script. And small scripts are stack items up to 4 bytes. And big script is everything larger than 4 bytes. And the issue is that arithmetic opcodes, they only work up to 4 bytes. So you cannot use any arithmetic opcodes with big script elements. And there is no way to cut big script elements down to small script elements. We would need like something like an opcode that is called split or maybe opcat or something like that. And since we don't have that, there is that fundamental problem of big script and small script. So if you have a big script element, there is no way to turn it into a small script element, and you cannot reason about it. You cannot do anything interesting with it, actually. And since that is the case, you cannot really do what you need to do to actually verify the gate garbling. And well, you cannot use the native opcodes. There are hash functions in Bitcoin that are just a single opcode and they hash a big script element, but you cannot use them to actually verify the gate or to disprove the incorrectly garbled gate. So what you have to do is to use like a hash function that is implemented in small script, and that is roughly on the order of 70 kilobytes of script. And you have to invoke this hash function, I think, 4 times or so. And that means in the end, you need like 4 times 70 kilobytes of script. So you end up with 280 kilobytes of script, which is almost on the same order of magnitude as BitVM2. So most of the gains that you actually got from garbled circuits are gone. And I came up with that new hash function that is like vastly more efficient in comparison to what we had previously for that use case. It's just like on the order of 1 kilobyte per invocation. But Yeah, that was an improvement over Jeremy's approach, and it made it way more practical. And since it's nicely simple, it's kind of like a cool approach. But now that we have all these other optimizations, like what I just mentioned with like half garbling and free XOR and all these CPU level optimizations for garbling and yeah, making the cut and choose very efficient, and even more so Liam's approach. All of that kind of made this hash function thing obsolete. So you don't really need that anymore. But it's kind of funny that you're asking about it because it reminds me of how fast the research is progressing in the garbled circuits for Bitcoin field right now. Because you read about it maybe a month ago or something, and it's already uh, old.
Yeah, that is very funny to hear because I remember the BitVM 3, your paper came out. Maybe it was like sometime over the summer, which was just a couple months ago. And it's so funny to see that since then so many changes have been made, and even that which was published just a couple of months ago is now considered to, or at least the bit hash part is considered to be a bit outdated. So very fun to see how fast these developments are moving.
Yeah, it's
Um,
very exciting.
yeah. And I also wanted to hear more about just some of the roles that are involved with BitVM 3. I was wondering, like, for example, you need someone to garble the circuit and then, or like create the garbled circuit. You need someone to publish that proof as well. So I'm assuming the garbler role like has that role. And then you also need someone to evaluate that as well. But wanted to hear if there's any like potential overhead that comes with that with like say for right now in the BitVM3 approach, you need someone to do that garbling. I was wondering if there was any kinds of trade-offs in terms of say like potential latency that goes with the overhead, or does um, the circuit size like efficiency component kind of make up for that? Just wanted to hear more about some of the trade-offs compared to prior BitVM constructions.
Yeah, to understand that, we maybe should first talk about the roles of the bridge. And there we have these operators and challengers. They can be the same people, but in general, they have different tasks to do. And the operators, they are the gobblers, and the challengers, they need to store the garbled circuit. And people in the BitVM Alliance came up with very clever approach such that you just need a single garbled circuit per operator challenger pair. So you can have infinitely many deposits with the same garbled circuit. So you just have that one-time setup cost. And that can be like a little bit expensive. I think even like the simple approach with like cut and choose and so on. I think for a single garbled circuit, it's on the order of like 5 hours or something to set it up. Um, so that is a bit costly in time, like not totally crazy. In the beginning, we thought about weeks, and now it's down to hours, which is quite great. Um, but it's a one-time cost, and since since that's the case, it's not really an issue.
Yeah, that makes sense. It's just one time. You don't need to kind of like make a new garbled circuit for any type of transaction that you're trying to create. So
Yeah,
that one-time setup cost, even though it may like, take those couple of hours, it's just one time, so it's not really too big of a concern.
yeah.
Okay, got it. Yeah, that makes sense. And then also was curious to hear about, like I remember you mentioned, at least for the hashing side, there were some difficulties, which led to the research into some new alternative hash functions, especially relating to how some native opcodes couldn't be used. But I'm just wondering, like for example, some of the popular opcodes that people are talking about, like for example with opcat. I'm curious to hear about some of your general thoughts on opcat, and if it is, say, enabled sometime in the future, how do you see BitVM evolving alongside with that?
Um, yeah, well, in general, I always said that BitVM is totally not the end game. It's actually a pile of hacks piled upon hacks to enable things that we actually should enable by opcodes. Um, and yeah, there are many different opcodes that people talk about, like or sets of opcodes even. Opcat is one of them. Opcat in particular would enable Stark proofs. Um, and also it would enable stateful covenants. Shall I explain what a covenant is? I guess people are not that familiar with Bitcoin. Um, so in Bitcoin, you have these UTXOs. So essentially, there are no accounts. There are coins. Everything is a coin, and there there often it's interesting to restrict how a coin is spendable. Currently, the only way to restrict how a coin is spendable is by signatures. So it's only spendable if I sign it. But it could also be interesting to say this particular coin can only be spent using this particular transaction or this particular template of transaction. And that is interesting because that essentially allows us to express smart contracts in Bitcoin. And it allows us to express state to some degree. And there are different kinds of covenants. There are like the most or like the most simple covenants. The proposal that is suggested for that is called CTV, check template verify, and that is very simple and it enables interesting things, but it doesn't really help with these bridges that we want to build. And if you want to build bridges, what you actually want is covenants that carry state. So essentially, a very simple example you could think of what that means is like you have some UTXO and you can spend it only with a transaction that kind of like creates the same type of UTXO again, but let's say it counts a counter up by one or something. And this way you can carry over state from one UTXO to the next. And that would be something completely novel in Bitcoin because Bitcoin, as it currently is, it's completely stateless. And with these kinds of new type of covenants, you could, for the first time, have UTXOs that actually carry over state natively. And yeah, Opcat is one proposal that would enable that. And Opcat is also kind of like scary to some degree because it's hard to say what it can do and what it cannot do. And it has been heavily pushed by people who are like kind of on the sketchy side of the Bitcoin community, um, and that's why it created a lot of resistance. They had also been like promoting like tokens that spammed the UTXO set, and like then the size of the UTXO set like doubled within 2 years or something, and so people became angry at them and. Then they started to like advocate for a consensus change, and then people got very resistant against that just because it came from them, and that kind of like killed the proposal to some degree. Like it's not that much of a hot topic anymore. It was a very hot topic, I think, a year ago or two. Now it cooled down a lot. Maybe it comes up again, but now it seems more likely that other proposals may get through. There are ideas like, for example, great script restoration. That is originally Bitcoin script was way more expressive, but the creator Satoshi he found a bug in one of the opcodes, and then he got super paranoid and deactivated essentially all of the good stuff. And great script restoration is the idea of re-enabling all of these opcodes. And yeah, some reputable developers are working on that. and that might be one path forward. Another path forward is a new language, like a completely new scripting language called Simplicity that is developed by Blockstream. It has been in development for quite some years, and just recently it got activated on the Liquid sidechain. So it is in production now, and that was a major milestone to actually also get it activated on Bitcoin. Um, it will certainly take some time for everyone to like wrap their head around it, and for people to actually agree on a specific proposal. But that would probably be the cleanest way forward, because then we could get rid of this quirky scripting language that we have right now that nobody understands, and that has like all these weird edge cases that are extremely hard to reason about. And yeah, if we had simplicity, it would become very easy to implement all kinds of proof systems in Bitcoin. With CAT, we can only implement actually Starks. We cannot really implement Snarks, because Starks, they rely like on mostly Merkle path verification, which is easy once you have CAT, and then you can use like the native of hashing opcodes. That also solves that big script, small script problem that I was talking about. Like, but long story short, it doesn't enable snarks, and since snarks are kind of like the industry standard when it comes to actually verifying a proof on chain, it would be interesting to also have snarks, and simplicity would enable all that, because it gives you like big script, sorry, big int arithmetic, and all kinds of high level primitives that would easily enable snark verification and stuff like that.
Got it. So the new kind of scripting language that was put into production, Simplicity, it has, at least on the proof system side, a lot more flexibility compared to, say, if, say, CAT were to be implemented in the future. I'd imagine if they're only able to enable Starks and you would need some sort of snark for an on-chain verification, then that Stark would have to be, I suppose, wrapped to a snark somewhere else for it to be enabled. So it seems like Simplicity provides a lot more like a flexibility and can enable for a quite a wider variety. And then just as a last question before we end today's session, just wondering about any kinds of future developments in research that you and your any collaborators you're working with are looking at right now, like for example, any kinds of alternative garbling schemes or any other types of optimizations or efficiency improvement techniques that you're looking into right now or want to look into for future work. Just any kinds of next steps that you see yourself taking in.
Um, yeah, there are definitely some interesting ideas floating around to make garbled circuits even more efficient. Um, I'm not quite sure how ripe these ideas are, but given like how much progress we made within like I think it was 4 months now, like since May we started working on that. Um, given we have made already that much progress, I'm quite confident that we will see even more breakthroughs within the next year or so. Uh, but I don't really have like concrete things to share right now.
Yeah, got it. But based on how many developments have happened in just the past few months, I'd imagine maybe when this episode is published, there would be even more developments that came out between the time that this was recorded and the time that this is published. So, yeah, when anything new comes back, would love to have you on again. But
Sure.
yeah, thank you so much, Robin, for coming in today and for sharing all of the insights behind the design considerations. Also very cool to hear about some of the origins with BitVM as well and how you leverage the optimistic verification technique, as well as all of those other kind of efficiency improvement advantages and techniques that you have looked into. A lot of thought has been put into designing this system. And yeah, very excited to see any kinds of future developments that happen. So thank you so much, Robin, for coming in.
Thanks for having me, Alice.
Yeah, thank you.